Okay, so this is calculating empirical formulas and molecular formulas. Uh, Defining both of them first, an empirical formula is a formula of a compound that expresses the lowest whole number ratio of the atoms. So basically, the subscripts are simplified as low as they can go. So subscripts are simplified or reduced as low as they can go, or reduced, I'll put in parentheses. So the difference between that and a molecular formula, the molecular formula is the actual formula of a compound showing the number of atoms present, the actual formula of the compound. If you look at the examples down below, we've got two over here or one over here on the left. It is C4H10. I'll rewrite it because in this format it doesn't look that great. So there's C4H10. And if you look at C4H10, that is the actual formula of that hydrocarbon. And so what we can do to that, if we wish to, is the 4 and the 10 can both be reduced. And the 4 and the 10 can both be reduced divided by 2. And if you do that, you end up with C2H5, and that would be an empirical formula because those subscripts down here at the bottom, they cannot be reduced any further. So that is your empirical formula, C2H5. On the right side, we have C6H12O6. That is the molecular formula, C6H12O6. And if we wanted to make this an empirical formula, we would have to reduce those subscripts down, the lowest whole number ratio of those subscripts. If you look at it, the carbon, the hydrogen, and the oxygen in this example can all be reduced divided by 6. And if we do that, we have our new compound CH2O, and that is the empirical formula from the molecular formula C6H12O6. Okay, so now what we want to do is we want to be able to calculate an empirical formula based on the masses of the elements in the compound. Okay, there are 4 steps that you're going to have to follow. Well, 3 steps, 4 steps if a certain situation arises. So the first thing that you have to do is determine, well, that's a big thick blue one in there, I'm going to change that, is the first thing you have to do is to determine the mass in grams of each element in the compound. And here we have 4.151 grams of aluminum with 3.692 grams of oxygen. So we know we're going to be using aluminum and we're going to have oxygen. We just don't know what the subscripts are going to be. So that's what we're trying to do right now. So the first thing is to determine the number of grams of each element in the compound, and we did. The second thing that you have to do is convert those masses to moles. And how you do that is by using your mole conversion chart and find on there moles and mass. Okay? And so if you're starting with mass, which is right here, and you're going to make that T-chart, you'll find that you have to perform this conversion factor, which is 1 mole of aluminum over the molar mass of aluminum. And so now you have a division problem. So when you divide 4.151 grams of aluminum by 26.98 grams of aluminum as the molar mass, you get the mole number 0.1539 moles of aluminum. Okay? And then for oxygen, you do the same thing. You take the mass that you were given, which is 3.692 grams of oxygen. You divide by the molar mass, which is right here of oxygen, so it's rounded up to 16. And when you do that, your answer becomes 0.2308 moles of oxygen. Okay? And again, that 16 represents the molar mass for oxygen. Okay, so now these numbers here are really, really important. That number is important, that number is important in starting to find out what our subscripts are going to be. So what we're going to do now is determine which one of these is the smaller number. So The third step in this is find the ratio by dividing each element by the smallest amount of moles. So here we have 0.1539 moles of aluminum, and here we have 0.2308 moles of oxygen. Well, this number happens to be smaller, so we're going to divide both of those numbers by the smaller number. So it turns out to be that 0.1539 moles of aluminum will be divided by 0.1539. And when you do that, you end up with 1 mole of aluminum, 1 mole of aluminum. When you do the same thing for your moles of oxygen as you calculated, so we have 0.2308 moles of oxygen, and we're going to divide it by the smaller number 0.1539 that we calculated. And when we do that, we end up with 1.5 moles of oxygen. Now, you cannot have decimals or fractions for subscripts. Those don't work, okay? That's not what we say is legal. Okay, so what we have to do is we're going to have to multiply the 1.500 moles of oxygen by a number to make this number a whole number. We want it to be a whole number, okay? We don't want the 1.5. So what we can do is we can multiply the 1.5 times 2, and that would give us a 3, okay? 3 moles of oxygen. And we can multiply the 1 mole of aluminum by 2, so because what you do to one number you must do to the other, and that will give us 2 moles of oxygen. Oh, I'm sorry, aluminum, okay? So 2 moles of aluminum, fix that. Okay, just like we have down here, we multiply by a common factor to get a whole number. Now, those numbers that we just calculated, the 2 and the 3, those are now going to be the subscripts for our aluminum and our oxygen in our formula. And so what it turns out to be is you can write down your aluminum and you can write down your oxygen. The 2 goes with the aluminum, so we write down the 2 as a subscript. The 3 goes with the oxygen, and so we write down the 3 with a subscript. Okay? And so now we have the empirical formula, Al2O3, aluminum oxide. Okay? Now there's one more way I want to do this. I'm going to go down over here and find the right one. Let's see. Yep. Here we go. This is it. We have these, we're calculating empirical formulas, but now we are giving percents of each element, okay? And so that's a little bit of a change. It doesn't change much, but it's a little bit of a change. So what we want to do is we want to change all of those to mass. Change the percentages to mass, and mass will always be in grams. Okay, so the way we do that is 63.38 is now going to become 63.38 grams of carbon. 12.38% nitrogen is going to be 12.38 grams of nitrogen. 9.80% hydrogen is going to be 9.80 grams of hydrogen, and oxygen will become 14.14 grams of oxygen. And that's what we need to start this process with. And you can see we have those numbers right here. Okay? So now we go to step 2. Step 2 says, take your mass of each element, the carbon, the nitrogen, the hydrogen, and the oxygen, and divide that by the molar mass of each element. Okay? So we have the molar mass of carbon here. We have the molar mass of nitrogen here. We have the molar mass of hydrogen. And we have the molar mass of oxygen. Okay? And when we do that, we get these numbers here. And this one right here is really supposed to be a 7, so I'm going to make that a 7 right there. Okay? 0.8837. So now the next step is to divide each one of those answers, each one of these answers underlined in green, by the smallest number that we see. The smallest number that we see is this one right here and this one right here. So we're going to divide every number there by the smallest number. And so that's step 3. So we go over here. Okay, so now we do that. We take our 5.302 moles of carbon, we divide it by 0.8837, and we get 6 moles of carbon. We take our 0.8837 moles of nitrogen divided by 0.8837, and we get 1 mole of nitrogen. We take our 9.72 moles of hydrogen divided by 0.8837, we get 11 moles of hydrogen. And 0.8837 moles of oxygen divided by 0.8837, we get 1 mole of oxygen there. And so now our molar ratio happens to be 6 to 1 to 11 to 1. 6 moles of carbon, 1 mole of nitrogen, 11 moles of hydrogen, 1 mole of oxygen. So our empirical formula becomes C6N-H11O. And that is how you calculate the empirical formula for that compound, giving the percentages of the elements in the compound.